Emma, do you want a bagel? This, by the way. No, we can't open this. Not right now.
All right. Problem 1754, everybody. 1754. Says a solution of calcium hydroxide has a measured pH of 11.6. What's the molar concentration of calcium hydroxide in the solution? What is the molar concentration of calcium hydroxide if the solution is diluted so the pH is 10.6? All right, so the pH is 11.6. Now, the component that changes the pH in calcium hydroxide is the hydroxide ion. So we need to identify the hydroxide ion concentration. All right, pH, this is the negative log of the hydronium, the hydrogen ion concentration. And we want to know the hydroxide ion concentration. So we can do this a couple ways. For me, it's easiest to convert or identify the pOH from the pH because that's just 14 minus 11.6. So the pOH is 2.4. Now we take, to find the hydroxide ion concentration, we take 10 to the negative 2.4, and that'll tell us the hydroxide ion concentration, which is 0.00398. That's the hydroxide ion concentration. For every hydroxide ion, though, you see here we're using calcium hydroxide, so you got to pay attention to that. The calcium hydroxide, it has 2 hydroxide ions for every 1 mole of calcium hydroxide, right? So we can pay attention to that and know that this is how many moles of hydroxide ion there are, and thus there's that divided by 2 moles of calcium hydroxide, or that's the molar concentration. This is the molar concentration of hydroxide ion, and that divided by 2, which is 0.00199, is the molar concentration of calcium hydroxide, right? Because there's 2 hydroxide ions for every calcium. What is the molar concentration of calcium hydroxide in the solution? It's that. What's the molar concentration of calcium hydroxide if the pH is 10.6? All right? So if the pH is 10.6, 14 minus 10.6. That's great. Want to come show everybody at home?
You're talking to your students.
Shh. So come over here. Little sister Scott just got her braces off. So she doesn't have any braces anymore. But she has to wear a retainer, right? Did they give you that yet? Okay. All right. Good luck. All right. So pH is 10.6. pOH then is 3.4. If pOH is 3.4, that means the hydroxide ion concentration is 10 to the minus 3.4. And that means that the hydroxide ion concentration for the second part of this problem is 3.9 times 10 to the minus 3.99 times 10, 3.98 times 10 to the minus 4. That's the hydroxide ion concentration. We divide that by 2. So it's about 2 times 10 to the minus 4 should be the calcium hydroxide concentration. So that was 1754. What? 1754. What is the molar concentration of calcium hydroxide if it's diluted to 10.6? So they just asked one question, and it's the 2 times 10 to the minus 4. 1754. 2 times 10 to the minus 3. Are we looking at the right problem here? 1754. What is the molar concentration of calcium hydroxide if the solution is diluted so the pH is 10.6? So they have 2 to the 10 to the minus 3. Let's make sure we're doing this right. So if the pH is 10.6 and the pOH is 3.4, then we can raise 10 to the minus 3.4 and we can get 4 times 10 to the minus 4, 3.98 times 10 to the minus 4, You divide that by 2 to get the concentration of the calcium hydroxide in solution. And let's see if I'm missing anything. If the solution is diluted so that the pH is 10.6, what's the molar concentration of calcium hydroxide? What's the molar concentration of calcium hydroxide in solution? 1754. Why do they only have one answer in the back there?
Bonus points for you.
They didn't answer both questions. Huh. I think that it should be 2 times 10 to the minus 4. Not 2 times 10 to the minus 3 like they said. So, I can look online later and find out if that one's mistake is one of the ones that has the problems. All right, 1756. In a 0.002 molar solution of sodium hydroxide, how many moles per liter of hydroxide come from the ionization of water? Okay. In a 0.002 molar solution of sodium hydroxide. So we have 0.0020 molar NaOH. Okay? Okay, so that's the concentration of sodium hydroxide. How many moles per liter of OH minus come from the ionization of water? How many moles per liter of OH come from the ionization of water? Well, we know that the ionization of water, the kW for water, is 1 times 10 to the minus 14. Right? And so the concentration of the OH minus ion times the concentration of the H plus ion are going to be equal to 1.1 times 10 to the minus 14. And so if we know that the concentration of hydroxide is 0.002, that's the concentration of hydroxide ion, the concentration of hydronium ion here, well, no, sorry. Because this is the concentration of the hydroxide ion, we can identify, if this is how much hydroxide ion there is, we can identify how much hydronium ion there would be in the solution. And then from that, we can identify how much hydroxide ion would be there as well. So, 0.002, that's sodium hydroxide. We can find the pH of POH. Find the POH first. So we take the negative log of 0.002. POH is 2.699 or 2.70. That's the POH. 14 minus that value. The pH of this problem would be 11.3. That means the hydrogen ion concentration would be 10 to the minus 11.3. So this hydronium ion concentration is 5 times 10 to the minus 12. And that means 5 times 10 to the minus 12 hydroxide ions would be dissociated as well. So that's the answer. 5 times 10 to the minus 12. What is the total? Let's see, 756. What is, how many moles per liter of the hydroxide ion come from the ionization of water? And this is the molar concentration of it. So 5 times 10 to the minus 12. So 1756. 1756. 5 times 10 to the minus 12. The molarity of OH from the ionization of water is 5 times 10 to the minus 12. Okay, so again, what we did there is we identified what the concentration of hydroxide ion was. We can identify the POH from that. We identify the pH from that. And from that pH information, we know how much hydronium ion there is, or how much hydrogen ion there is. And all the hydrogen ion that exists had to be due, or for that same amount, there has to be the same amount of hydroxide ion in solution. Okay? You see that this number is so small that it doesn't even contribute to the significant digits there. 1758. A solution that was prepared with 2.64 micrograms of barium hydroxide in 1 liter of water. What is the pH of the solution, and what concentration of hydrogen ions is provided by the ionization of water? So we have 2.64 micrograms of barium hydroxide. Barium, what is the... we have to look, I'm going to try to find the molar mass of barium hydroxide. Barium, 137.33. Barium, and then there's 2 oxygens. 2 oxygens, 216, that's plus 32. So 137.33 plus 32, and then 2 hydrogens. 2.002. All right. 171. All right, so that is a molar mass of barium hydroxide, and that's how many grams there are per mole. And we said that we added 2.64 times 10 to the minus 6 grams, right? Or 2.64 micrograms. So 101 mole is 171.33 grams. We added 2.64 times 10 to the minus 6 grams. So this will tell us how many moles there are, and it says that it's in 1 liter. So this will tell us how many moles per liter. So this is 2.64 times 10 to the minus 6 divided by 171.33, and that tells us that the molarity, divided by 1 for the molarity, it's 1.54 times 10 to the minus 8 molar barium hydroxide. That value times 2, because there's 2 hydroxides, will be the molar concentration of the hydroxide ion, which is 3.08 times 10 to the minus 8. Okay, so let's see. Just want to check one thing out here.
Yeah. That get us to Peter.
I'm just going back to page 176 and looking at the rules for barium hydroxide. So, all metal hydroxides are insoluble except for group 1A and those of calcium, strontium, and barium. So, barium hydroxide is soluble. So that's a fair assumption, right? That the amount of barium hydroxide, the molar concentration times 2 would be the molar concentration of the hydroxide ion. Okay? Alright, so 1758, finishing this one up. What is the pH of the solution, and what concentration of hydrogen ions is provided by the ionization of water? So what's the pH of the solution? Well, if this is the hydroxide ion concentration, we can take the negative log of that value right there, and that will give us the pOH. We can take 14 minus that value, and we'll see that the pH is 6.4. So this was the hydrogen ion concentration. Or sorry, the hydroxide ion concentration. We took the negative log of this value, and we got the POH, or POH, yeah, 7.5. We took the 14 minus 7.5, and we got the pH. So according to this, it would suggest that the pH is 6.4. And that's a problem because 6.4 is slightly acidic, right? We just added hydroxide ion, and so it shouldn't be slightly acidic. So we have to also take into account the auto-ionization of water, because you see that this value is smaller than how much water auto-ionizes. Alright, so if we have the auto-ionization of water here, we can identify this pH here, 6.4, and we can take if this is what the pH is here, we can take 10 to the minus 6.4, so 10 to the minus pH, 10 to the minus whatever the pH is, will tell us the concentration of the hydrogen ion in solution. So that is 3.98 times 10 to the minus 7. Can you see this? Can't see that. 3.98 times 10 to the minus 7, that's the hydrogen ion concentration. So if we take 1 times 10 to the minus 14 and divide it by this value, and that'll give us the hydroxide ion concentration. So from that hydroxide ion concentration there, and we can add it to this hydroxide ion concentration there, 3.08 times 10 to the minus 8. So now the sum of those would be 5.59 times 10 to the minus 8. And what's the question again? 1758. What is the pH of the solution, and what concentration of hydrogen ion is provided by the ionization of water? Alright, so let's take a look here. pH of the solution, 6.49. The amount that's added by the auto-ionization of water, 3.2 times 10 to the minus 7. Was that the value we got? 3.2 times 10 to the minus 7. Let's double check that one. Can you push stop there, Sam? Okay, so problem 758. A solution was prepared with 2.64 micrograms of barium hydroxide. So barium hydroxide, we have to find the molar mass of barium hydroxide. Barium is 137.33. So 137.33 plus 16 plus 16 plus 2.002. So that's 171.332. That's grams per mole of barium. So 1 mole of barium hydroxide is 171.332 grams of barium hydroxide. And we added, it says 2.64 micrograms, so that's times 10 to the minus 6 grams, and we put it into 1 liter of solution. So that gives us in the end moles per liter. Grams cancel out, we're left with moles per liter. So if we solve that problem there, we'll take 2.64 times 10 to the minus, times 10 to the minus 6 divided by 171.332, and that value there is 1.54 times 10 to the minus 8, and that's the molar concentration of barium hydroxide. But there's 2 hydroxides for each one, so we have to multiply each barium hydroxide, so we have to multiply that by 2 to know the final hydroxide ion concentration. 308 times 10 to the minus 8 molar hydroxide ion. Alright? So, that's the concentration of hydroxide ion. We can find the pOH by taking the negative log of that value. And the pOH, it says, is 7.5. And we can take 14, subtract the pOH, and it'll be, the pH then says it's going to be 6.5. And if you look in the back, let's see, 1758, 6.49 or 6.5, right? And 3.2 times 10 to the minus 7. What was the other part of the question? What is the pH of the solution, and what concentration of hydrogen ions is provided by the ionization of water? So that would be just the, let's see, we have pH 6.5. All of it is provided by this pH. Let's see, the negative log then, no, 10 to the minus 6.5. That gives us 3.16 times 10 to the minus 7. And 1758, 3.2 times 10 to the minus 7. So according to this, that's how they, that fits the answers in the back of the book. Unfortunately, this doesn't make a lot of sense because we took a solution, a liquid, a water, we just took water, and we added barium hydroxide. Barium hydroxide is a base, right? We added a base. We didn't add very much of the base, but we did add a base, right? So we wouldn't expect the pH to go down, right? That 6.5, the water was pH about 7. We added base and it went to 6.5, made it more acidic. That doesn't make any sense, right? We added base, so the solution needs to become acidic somehow. So this is where, when you're making very, very, very dilute solutions of acid or base, and you solve problems like this, you won't get the right answer because the auto-ionization of water contributes to the pH itself. So, according to this is the amount of acid that will be produced, but this is the amount of base that is made. And we know that the auto-ionization, so I'm going to erase this top part up here for a second. I mean, this is how, that's where the answer ends at the back of the book. But if anybody were just to take a few seconds and look at that, they would say there's something wrong there, right? And you'll learn about this more in analytical chemistry and maybe further on in this chapter. But we know that 1 times 10 to the minus 14 is the auto-ionization constant for the concentration of hydroxide ion and water, or hydronium ion, sorry, hydrogen ion. So we know that if this is how much base this is the amount of base that has been provided by the hydroxide, by the barium hydroxide that we added, 3.08 times 10 to the minus 8, right? And we know that the hydroxide ion, according to this ionization, will give 1 times 10 to the minus 7, right? But this already contributed some. So we can take this much. We know that this much is how much it's going to produce. It's going to go up to that amount. So we can take this value here, and we can subtract it from this value. So we take our 1 times 10 to the minus 7, because that's how much base is going to auto-ionize in solution. We subtract it from how much base has been contributed, and that's 3.08 times 10 to the minus 8. And that gives us 6.92 times 10 to the minus 8. 6.92 times 10 to the minus 8. So that's how much base is still left to auto-ionize from the water. And because of that, that's also going to be how much acid will auto-ionize from the water. And that is what's going to govern the acid concentration. So the real acid concentration will be that. So if we take the negative log of that value, then we see that the pH is now 7.16. And that is what truly would happen. And the pH of this solution, after you added barium hydroxide, obviously it would be basic. And yes, it's a very, very, very small amount, and it will become only slightly basic. So this is the new pH. All right, so that's 1750.
Where is that?
All right, so that's 1758. Now we'll go on to 1760. A 0.1 molar solution of acetic acid has a pH of 2.37. 1 molar acetic acid, right? So the acid is 1 molar acetic acid. That means we take a container. Here's the container. It's mostly water, but we put in enough acetic acid to make it 1 molar acetic acid, right? But the pH doesn't reflect that. I mean, obviously acetic acid is a weak acid, so the change in the pH due to that acid is not going to be complete, right? If it was 1 molar HCl, then the amount of acid would be 1 molar as well, because every mole of acid would dissociate. Therefore, the concentration would be 1 molar H plus, and that is a pH of 0, right? Okay, so, but that's not what we have here. We have 1 molar acetic acid, but the pH is 2.37. And then the question asks, question 1760, what percentage of the acetic acid is ionized in the solution? Well, we know that we have 1 molar acetic acid, and 2.37 indicates the molar concentration of the H plus ion. So we can take 10 to the minus 2.37, and that is 0.0042 molar H plus ion. All right, so that's how much H plus ion we have. This is how much acetic acid we have, and then we want to know what percentage of the acetic acid is actually ionized. Just take this value, put it over the 1, and multiply by 100, right, to get percent. So that's 0.427 molar. 0.427%. 0.427%. So this is 1760. 1760. 0.43. So they went into two single figures. All right. So 1762, the Ka for hydrofluoric acid is 6.8 times 10 to the minus 4. So let's see, can you see that there? Yeah. What's the Kb for the fluoride ion? 6.8 times 10 to the minus 4. Well, just like the concentration of the hydronium ion and the concentration of the hydroxide ion are, their products are 1 times 10 to the minus 14. The products of the Ka for an acid and the Kb for its conjugate base, those products also have a sum of 1 times 10 to the minus 14. So 1 times 10 to the minus 14 will equal the Ka for the acid and the Kb for its conjugate base. The product of those two. So this is the Ka for the acid, and this is what we have. And this, the acid is HF. And this will be the Ka for HF, and this will be the Kb for the conjugate base, F minus. All right. So we can just take 1 times 10 to the minus 14 divided by 6.8 times 10 to the minus 4. All right. So the Kb then is going to be 1.47 times 10 to the minus 11. All right. 1764. Lactic acid is responsible for the sour taste of milk. Ka at 25 degrees is 1.4 times 10 to the minus 4. What's the Kb, the conjugate base, the lactate ion? So again, we just do 1 times 10 to the minus 14 equals 1 Ka times the Kb for its conjugate base, and Ka is 1.4 times 10 to the minus 4. So the Kb can be solved by solving there. And what else? Is its conjugate base a stronger or a weaker base than the acetate ion? The acetate ion. Well, let's see. What were we told about the acetate ion? We need to know the Ka for the acetate ion. Where do we have the acetate ion? Let's find out what this one is first. 1 times 10 to the minus 14 divided by 1 times 4 times 10 to the minus 4. So we have 7.14 times 10 to the minus 11. That's the Kb for the lactate. And so we need, I don't remember them telling us the Ka for acetic acid in a recent problem or anything, so we have to look through the book and find out what the Ka for acetic acid is. Alright, and there should be a table of common Kas back here. Okay, so here is on page 781. We have some common Kas. There's acetic acid. There's the formula. There's the Ka. It's 1.8 times 10 to the minus 5. To find the Kb, we take 1 times 10 to the minus 14 and divide it by 1.8 times 10 to the minus 5. So the Kb for, this is the Kb lactic acid, and this is the Kb acetic acid, and this one is 5.5 times 10 to the minus 10. So this value is smaller, right? Lactic acid is smaller. So the question is the lactic acid, the lactate ion, a stronger base than the acetate ion, the acetate ion, right? And we would see that because this value is larger or smaller, then it's a weaker ion, right? So this value is smaller, therefore it's a weaker ion. And let's see, 17.64, the value up here, we got 7.1 times 10 to the minus 64, where's it at? 10 to the minus 11, yeah. Okay. You done, Tom? Okay. So 1764. We mentioned that if the Kb was smaller, if the Kb is a smaller value, then it's a weaker base, a weaker base. And we can think about this way, right? The Kb for a base is such that, so this will be the acetate ion, okay? So I'll just write, well, there's the acetate ion. And the acetate ion acting as a base to pick up a proton, right? Here it's acting as a base, picking up a proton and forming acetic acid, C2H3O2H, right? So it's acting as a base, picking up the acetic acid. The Kb would be then the C2H3O2H concentration over C2H3O2 minus times the H plus concentration, right? So the Kb would be the equilibrium constant that represents this picking up the proton. The Ka is the opposite, right? It would be the reverse arrow here. of this acid releasing the proton, right? The equilibrium constant at which this acid is going to be released. Therefore, if our Kb here is a very large number, that means there is a lot of this, right? Or that this concentration is very, very small. This concentration is very small. And if this concentration is very small, that means this was good at taking that proton and it made this, right? So the larger this number is, the better the base was at taking the proton. So if our Kb is very large, then that means it's a good base. If our Ka is very large, it means it's a good, or it's a stronger base if it's large. If its Ka is very large, it's a stronger acid. So if we're comparing Kas for acid, larger the Ka, the stronger the acid. Again, comparing Kb's for bases, because this is what the definition of the Kb is, the ion picking up an acid and acting as a base, right? Therefore, the larger the Kb, the better the base. (1766). Sam, can you help Tom out a little bit? A 0.2 molar solution of acetic acid, or no, of a weak acid, HA, has a pH of 3.22. What is the percentage ionization of the acid? What is the value of Ka for the acid? So we have a 0.2 molar solution of a weak acid, pH 3.22. 0.2 molar, right? We can find out what percentage of it, of the acid, is actually there by taking the pH. 10 to the negative 3.22. The actual concentration of H plus ion from this acid being in solution is 6.02 times 10 to the minus 4. Take it to mommy. He loves those drinks, Mom. Alright. 6.02 times 10 to the minus 4. And there's 0.2 molar. So this is molar, right? And out of 0.2 molar. So if we take the 6.02 over 0.2, that'll give us what, tell us what percent. Or not, that'll give us the fraction, and then we multiply that by 100. And that tells what percent is actually ionized. And the percent there is 0.301. Alright, so we'll double check that in the back. 1766. 1766.301, or 0.30% is ionized. And then the question is, what's the question there? What is the value of Ka for the acid? The value of Ka for the acid, well, Ka, right, represents the acid deprotonating and becoming H plus and A minus. Correct? And we know the initial concentration here of the HA that we put into solution was 0.2. So the Ka for this is the concentration of the H plus times the concentration of the A minus over the concentration of HA. And we know how much HA we initially put in. Well, this isn't initially, this is at equilibrium, right? So we can do a little ice table here. And initially, we put in 0.2 molar of the HA, and we had none of this, correct? Some of this is going to be removed, minus X, and the same amount, plus X, is going to be added for both of these, right? And so at equilibrium, this is going to be 0.2 minus X, and this is going to be X and X. And we know that based on the pH, the concentration, based on this pH, the concentration of the H plus ion was 6.02 times 10 to the minus 4. So we know that this X here is actually 6.02 times 10 to the minus 4, and this one has to be the same. And this minus 6.02 times 10 to the minus 4. Right? So we can put those values into here, And we know that this is 0.2 minus 6.02 times 10 to the minus 4. And that this up here is 6.02 times 10 to the minus 4 squared, right? So we can identify the Ka from the information given. So we have 6.02 times 10 to the minus 4 squared divided by 0.2 minus 6.02 times 10 to the minus 4. So that means Ka equals 1.8 times 10 to the minus 6. All right, double check there, 1766, 1.8 times 10 to the minus 6. So again, the way we did that is we set up what Ka was equal to. All right, so I'll rewrite it up. Well, 6.02 times 10 to the minus 4. Ka is equal to, it's equal to the amount of H plus times the amount of its conjugate base over the, not the initial concentration, but the equilibrium concentration of HA. We know the initial concentration of HA was 0.2. We know the final concentration of H plus is 6.02 times 10 to the minus 4. Therefore, final concentration of A minus is also 6.02 times 10 to the minus 4. And the final concentration of HA must have been 0.2 minus this 6.02 times 10 to the minus 4. So then we can put that in, solve that value, and find out what the Ka equals to. All right, that's 17.66. $17.68. Periodic acid, HiO4, is an important oxidizing agent and a moderately strong acid. In a 0.1 molar solution, the H plus concentration is 3.8 times 10 to the minus 2 molar. Calculate the Ka and the pKa for the periodic acid. All right, so the definition of Ka for this acid, Hi, right? H plus, the ionization, I minus, is the concentration of H plus times the concentration of I minus. Oh, it's not I minus. What is it? IO4 minus. All right. Ka equals the concentration of hydrogen ion times the concentration of IO4 minus times the over the concentration of HiO4. Okay. In 0.1 molar, so if we put in 0.1 molar, all right, I'm going to erase this right here. Put in 0.1 molar, 0.1 is how much we started off with, and we lose the H plus concentration in that solution is 3.8 times 10 to the minus 2. 3.8 times 10 to the minus 2. And this up here is 3.8 times 10 to the minus 2. That's the concentration of H plus ion, so they told us. And that'll essentially, consequently be also the concentration of the iodic ion. All right, for the periodate ion. 3.8 times 10 to the minus 2. Yeah. All right, so the solution of this will be the Ka for this periodic acid. And they also want to calculate the pKa for periodic acid, the pKa. All right, so we can identify the Ka. Let's solve this here. 3.8 times 10 to the minus 2 squared divided by 0.1 minus 3.8 times 10 to the minus 2. All right, so Ka looks like it's 0.0233. And so that's calculate the Ka. Let's see if we're right on that one. 1768. 2.3 times 10 to the minus 2. And then we also have to identify the pKa. And we already talked about what the P means. It's just a function. Just like pH, anytime you want to take the P function of something, you just take the negative log of it. So the pKa of this, pKa, negative log of that value